Hello, and welcome to this session on AutoML, the future of machine learning. My name is Mark Hornick, Senior Director of Oracle Machine Learning Product Management at Oracle. Many machine learning software tools are sporting some form of automation for the modeling process. But is this AutoML really the future of machine learning and artificial intelligence? I suspect that many of you may agree that having a fully automated machine learning process would be welcome to most project managers and executives. But while a significant part of the machine learning process can be automated, there are limits we face today that we'll explore in this session. We'll also look at the AutoML capability included with Oracle Machine Learning for Python and the AutoML no-code user interface. This is Oracle's safe harbor statement, since we'll be talking about some pre-release features. So let's start with imagining what a project manager might want, or at least imply. Imagine you have a genie that you can command to solve your business problem. AutoML fulfills the command solve my business problem and gives you insights and generates profits. But unfortunately, it's not that simple. At least not yet with the current technology. A more practical approach is to have a cleanly defined business problem, such as predict customer lifetime value, where the goal is to better understand which customers are our most important, using well-understood data. Then we can apply machine learning to produce a machine learning model that predicts customer lifetime value. But the real question about whether AutoML is the future of machine learning doesn't just hinge on building a model, but addressing the broader machine learning process. As we'll discuss, some aspects of machine learning can readily be automated, while there are others that are still under active research. In a sense, we can view a business problem as a puzzle, with a variety of pieces that need to fit together. Here, the pieces correspond to the machine learning process phases. First, we start with business problem definition. This really isn't the realm of AutoML, at least not today. Although there are a range of common business problems in any given industry, such as customer attrition, demand forecasting, and customer segmentation, just to name a few, this part of the process normally requires business-specific domain knowledge to define the problem and success criteria that will address a specific business need. Today, and likely for the foreseeable future, humans are critical for that. Next comes data understanding. Again, this requires business-specific domain knowledge to locate and relate data from possibly diverse and inconsistent systems. Today, humans are critical for that task as well. Then we get into the gray area of data preparation. I call this a gray area because some aspects can be automated, while others are less likely. For example, on the positive side, there are algorithm-specific transformations involving binning, normalization, outlier treatment, and missing value handling that can largely be automated. There is even creation of derived variables, also referred to as feature engineering, such as extracting features from date data or constructing interaction terms that can be readily automated. However, on the negative side, business-specific domain knowledge is required to match data across systems or to recode synonymous values. In still other cases, some feature engineering relies exclusively on human ingenuity to combine features in creative ways, often leveraging domain knowledge, and this is an area of active research. Then we get into the machine learning phase, or modeling. And this phase expects that the data is assembled and prepared, ready for applying algorithms. This has three key steps: selecting the algorithm or algorithms to use, selecting the set of features to use with each of these algorithms, and tuning the algorithm hyperparameters to get a better or best model. The modeling phase is where automation typically applies today. While it's straightforward to automate model selection using objective quality metrics like accuracy, If the business needs model transparency, for example, why and how predictions are made, it may be a subjective, that is, a human decision as to which model offers the best interpretability. Modeling is followed by the phases of evaluation, deployment, and monitoring. And once we have our models, we need to assess whether the original business problem is addressed, and if the success criteria are likely to be met. The selected model is then made part of an overall solution, which is deployed in the business, perhaps integrated with applications or dashboards. Once deployed, it's essential to monitor the results and assess if the success criteria continue to be met, and if not, take corrective action, which may involve simply rebuilding the model or exploring additional data sources. While tools can assist with each of these last three phases, humans will likely remain engaged for the foreseeable future, especially in certain industries like healthcare or finance. Since the modeling phase is the most readily amenable to automation, let's focus our attention here. We can think of modeling as consisting of three phases: algorithm selection, feature selection, and model tuning, where each can involve an iterative process to explore the solution space and evaluate individual models. Normally, advanced knowledge of machine learning algorithms is essential to get superior quality models. For example, each algorithm may have specific requirements for data preparation, or provide a range of settings known as hyperparameters that need to be explored. It's here that developing machine learning models is often time and resource intensive. So let's look at two aspects of machine learning complexity in more detail: data preparation and algorithm hyperparameter tuning. Here's a list of some of the more common data preparation techniques. These range from data cleaning and feature selection to feature engineering and reduction. Some of the complexity is highlighted by basic questions like, well, which transformations are needed for my specific data? Or which transformations are required for a given algorithm? For example, some algorithms require all numeric data to be binned or normalized. Others require categorical data to be converted to numeric or one-hot encoded. Some are sensitive to outliers, while others are sensitive to missing values. It's relatively straightforward to apply some of these transformations automatically. In Oracle Machine Learning's in-database algorithms, automatic data preparation handles the required algorithm-specific transformations, such as binning and one-hot encoding. In other cases, multiple transformations could be applied, with those adding the most value being automatically selected to include during model building. Other aspects of data preparation, however, are more subjective. For example, recoding synonymous values and deriving new variables normally requires domain knowledge or understanding of the quirks in the data. Next, let's consider algorithm hyperparameters. That is, the settings we can specify for an algorithm that impact model quality and performance. Here are two examples. On the left, we have open source documentation from scikit-learn for the support vector machine algorithm. We see quite a range of hyperparameters, like C and epsilon. Should we choose C as 1 or 0.1, or maybe 2? Or epsilon at 0.1 or 0.2, or maybe small increments between these values. On the right, we show the hyperparameters for AutoML's generalized linear model algorithm and see the options and possible value settings. Should we enable feature generation, and which feature selection criteria should we choose? Perhaps we should build models with each setting and compare the results. Well, I think we can quickly see the combinatorial explosion of the search space. While we could script outer loops to try all possible combinations, this would take a long time and consume a lot of compute cycles. Of course, we'd also need to automate the model selection process, since we don't want to evaluate each model manually. So what can we do? Well, solutions to the pain points just discussed obviously involve eliminating repetitive tasks, such as model building and evaluation through automation, with the goal to increase user productivity. This can include basic algorithm-specific data preparation, such as normalization, binning, and one-hot encoding. To the extent possible, we should apply machine learning to the machine learning process itself to automatically zero in on the right algorithm, features, and hyperparameters necessary to build high-quality models, without resorting to exhaustive search. Such automation helps to make machine learning more accessible to a broader audience and can reduce the compute time and cost required to get to the desired result. So, what machine learning tools does Oracle provide in this context? We'll enter Oracle Machine Learning with Oracle Database and Oracle Autonomous Database. Oracle Machine Learning is comprised of a family of components supporting data science projects involving a range of personas. These include, of course, data professionals, such as data scientists and data analysts, but also application and dashboard developers who need to consume the results of machine learning. Oracle Machine Learning provides interfaces for three popular languages: SQL, R, and Python. And as we mentioned earlier, the in-database algorithms have built-in automation for algorithm-specific data preparation. The Python interface, which we refer to as OML for Pi, includes AutoML capabilities for in-database model building that we'll cover in more detail shortly. We should note that Oracle's OCI Data Science also provides AutoML capabilities for select open source algorithms. However, for this session, we focus on in-database AutoML. For interaction with Oracle Autonomous Database, we provide OML notebooks. This provides a collaborative user interface based on Apache Zeppelin technology, further extending Oracle Autonomous Database as a data science platform. Data scientists, analysts, developers, and DBAs can use both SQL and Python in the same notebook, using the most appropriate language for the problem at hand, and view notebook changes by team members in real time, interactively. These same data science team members can explicitly share notebooks and templates, granting access permissions to other users, while also versioning notebooks and scheduling notebooks for execution. Oracle Data Miner user interface is a SQL developer extension that enables on-premises and DBCS users to create, schedule, and deploy analytical workflows through a drag-and-drop interface. It too provides some automation for building and comparing multiple models and generating SQL-based deployment code. Oracle Machine Learning for Spark provides machine learning in the big data environment with scalable, parallelized algorithms. Coming soon are the Oracle Machine Learning AutoML UI, a no-code user interface that automates model building, selection, and deployment, which we'll see in more detail shortly. Also coming soon is Oracle Machine Learning Services, which provides a REST interface for model deployment and management, along with cognitive text analytics. Both AutoML UI and OML services will be available as part of Autonomous Database. Now let's take a closer look at automatic machine learning in OML for Pi. Here, AutoML increases data scientist productivity while reducing overall compute time and enables non-expert Python users to leverage machine learning. This is in part because they do not need to be experts in the modeling process. The range of algorithms with their corresponding data preparation requirements, or understand each algorithm's hyperparameters. OML for Pi's AutoML consists of three steps we discussed earlier: algorithm selection, feature selection, and model tuning. With automatic algorithm selection, the goal is to identify the in-database algorithms likely to achieve the highest model quality. Using meta-learning, AutoML leverages machine learning itself to help find the best algorithm faster than with exhaustive search. With automatic feature selection, the goal is to denoise data by eliminating features that don't add value to the model. By identifying the most predictive features and eliminating noise, model accuracy can often be significantly improved, with the side benefit of faster model building and scoring. Automatic model tuning tunes algorithm hyperparameters and can significantly improve accuracy while avoiding manual or exhaustive search techniques, which can be costly both in terms of time and compute resources. We'll first look at some of the API functions and then see a demonstration using AutoML to build a classification model. Let's take a look at some of the OML for Pi AutoML functions. As we said, automatic algorithm selection can identify the best algorithm. But what do we mean by best? Well, algorithms are ranked based on a score metric, and the one that achieves the maximum score metric value is normally selected. Choosing from the set of candidate in-database algorithms, machine learning guides algorithm selection through data characteristics with advanced meta-learning techniques. Looking at the API, first we create an algorithm selection object, indicating the mining function, here classification, and the score metric, accuracy. We can also specify the desired degree of parallelism. Invoking the select function with the training data provides a ranking of each algorithm and corresponding score metric that we can use in subsequent steps. Additional arguments include, for example, the case ID, a column name that aids in sampling and splitting the dataset, K, which indicates the number of top algorithms to return, and the time budget, which indicates in seconds how much effort should be spent. Note, however, that if the budget is too low, the ranking scores may be incomplete. Depending on the mining function, OML for Pi's AutoML supports a variety of score metrics specific to binary or multi-class classification and regression. These can be used in the selection of algorithms, features, and models, as well as model tuning. The next step is automatic feature selection, which can speed up the machine learning process by selecting the most relevant features to be used in our model. Here, we create a feature selection object, specifying the mining function, score metric, and degree of parallelism as before. We then invoke the reduce function and specify the algorithm, likely selected from the previous ranking, since the features selected are typically dependent on the specific algorithm. Here, we specify DT, the decision tree algorithm. The argument adaptive sampling controls dataset sampling to reduce overall runtime, which is true by default to improve runtime performance. We can then see the selected features and create a subset of predictors to be used for model tuning. Automatic model tuning, which can significantly improve model accuracy, is also guided by machine learning. It uses a highly parallel, asynchronous, gradient-based hyperparameter optimization algorithm to tune the hyperparameters for a given algorithm and training data. And this avoids manual or exhaustive search techniques, as we mentioned earlier. Here, we create a model tuning object specifying the mining function, score metric, and degree of parallelism. We invoke the tune function, again passing the algorithm, and the training data, with features selected from our previous step. The param space argument specifies the search ranges for each hyperparameter if we want to specify them. We'll give some examples that would replace the ellipsis shortly. Another optional specification, CV, allows users to specify the cross-validation splitting strategy. If set to auto, the cross-validation folds are determined based on the size of the dataset. Large datasets don't need to use cross-validation. If set to an integer value, this specifies the number of folds. A value of none will allow specifying validation data explicitly. In the results object, we can get the best model or look at the evaluation of all the models that were tried. For the param space argument, where we specified the ellipsis for the value in the previous slide, here we show some possible values for decision tree and neural net algorithms. For example, with decision tree, a user may want to control the search space for the minimum % of records in a terminal node, here shown with a range between 0.01 to 10%. Or for neural network, we may want to control the number of hidden layers explored, here being shown limited to 1 and 2 hidden layers. Each of the in-database algorithms have a set of hyperparameters, and these are chosen automatically by the system. But the user can specify these for greater control over the search space. These can be used to restrict or expand the search space as required. Let's have a quick demonstration of AutoML as provided in OML for Pi. Here, we're looking at the OML Notebooks interface with our AutoML classification demo notebook. So first, we're going to run the Python interpreter to import OML and other libraries, and implicitly connect to the database using OML for Pi. Then we prepare the wine dataset from sklearn datasets before we create the database table using OML create. This creates the wine table in our autonomous database and returns a data frame proxy object. We see the table shape and the column data type. Here we can view the first few rows of our table. Note that our target column on the far right is called target. And next, we'll prepare the data, separating predictors from the target, as is the Python convention. Now we're ready for automatic machine learning, starting with automatic algorithm selection. We define our algorithm selection object and invoke select using our wine predictor and target proxy objects, and indicate that we want to return the top 4 algorithms. Once this completes, we display the selected algorithms and their predicted accuracy. Here we see SVM Gaussian is the top model with about 98% accuracy. For feature selection, we create a feature selection object, again choosing classification for our mining function and accuracy for the score metric, and that we want parallelism of degree 2. We then invoke reduce with the top algorithm, SVM Gaussian, and provide our wine proxy objects. Here we see that AutoML has selected 9 of the 13 predictors to be included for this algorithm. Next, we move to automatic model tuning, where we create a model tuning object and then invoke tune, not only with the selected algorithm, but also using the reduced set of predictors from the previous step. And here we see the resulting SVM model. As we discussed a moment ago, users can also explicitly provide search space parameters for model tuning. And here we're providing hyperparameters for a random forest model, where we specify ranges for the sampling ratio and number of trees, as well as the tree impurity metrics. We invoke tune and provide this search space. And then we see the resulting random forest model. In our last example, we see how automatic model selection combines both the algorithm selection and model tuning in a single convenient function, further streamlining the process. Here we create our model selection object and invoke select with the original wine data, indicate that we want the top model tuned, and invoke cross-validation with 2 folds. Here we see the SVM Gaussian model was also selected. So in this demo, we've highlighted how AutoML takes on the heavy lifting for selecting algorithms and features, as well as tuning models that are then ready for deployment. While data scientists may reach for AutoML programming interfaces, such as found in AutoML for Pi, as we just saw, another new component coming soon is the AutoML UI, a no-code user interface supporting automatic machine learning. It supports both data scientist productivity and non-expert user access to powerful in-database algorithms for classification and regression. Oracle Machine Learning AutoML UI automates model building with minimal user interface. Just specify the data and the target in what's called an experiment, and the interface does the rest. As we'll see next, running an experiment produces a leaderboard of models and their performance, and allows users to select models for deployment in REST endpoints in OML services. Here's a quick demonstration of AutoML UI. We're looking at the home page for OML notebooks. Let's click on the AutoML Quick Action link. And this takes us to the AutoML experiments, where we're going to create an experiment, provide a name for our experiment, affinity card, and choose the data source we'll use to build our models. In this case, customer demographics, which is a table in our autonomous database that's already been prepared. We specify we want to predict the column affinity card, indicating that we should offer an affinity card to a given customer. We also provide the customer ID column as the case ID. Now we can see the available features, and we can explicitly deselect features if we have some that we don't want to use. We also have additional settings. For example, we can specify the algorithms we'd like to try. For our demonstration, we'll deselect a few of these. We also can set the number of top models to return. We'll set this to 3. Now when we press start, we can choose faster results or better accuracy. We're going to choose faster results. We click here to pop up the progress bar and see the various phases the experiment will go through. First is algorithm selection, where we'll see which algorithms should be tried and what their initial accuracy metric is. Then we have adaptive sampling and feature selection, followed by model tuning, where we see that 3 algorithms will be tried: naive Bayes, random forest, and decision tree. And we can see on the left that we are increasing our accuracy progress. This gives you a feel for how the model accuracy is progressing over time. And in the leaderboard, we see the model accuracy being updated, first with naive Bayes, as more models are tried, and then with random forest. Decision tree is the last one that's being worked on. The final phase is feature prediction impact, and this gives a model-agnostic sense of the relative importance of features when making predictions. So let's look at some of the details of our models. We'll start off with naive Bayes, and we see household size is the most important, followed by bookkeeping applications. Next, we can look at the confusion matrix, indicating the type and quantity of errors made by our model. Looking at the random forest model, we see its feature ranking and confusion matrix. Let's click Deploy for our naive Bayes model. In this case, we'll provide a name, a URI, and a version number. This deploys the model to OML services. From here, we go to the Models interface. And we'll see the set of user models produced by our experiment. If we go to deployments, we'll see our named model, Naive Bayes affinity card. And by clicking on that, we see the model metadata. And on the URI, we'll see the Open API specification. And this is now ready to be used through our REST API. So let's go back to our experiment listing, where we not only create new experiments, but we can edit, duplicate, start, and stop experiments as well. Let's open the affinity card again and select a model such as Naive Bayes and click Create Notebook. This is going to generate the code that will allow us to recreate this model in an OML notebook. We specified Affinity Card Notebook 1 as the notebook name, and then let's go and open that notebook. We see the AutoML UI generated code for building the Naive Bayes model and invoking predict on that model. So this concludes the AutoML UI demo. So we started this session asking, is AutoML the future of machine learning, where AutoML truly becomes our genie to solve business problems? It's clear that we can automate some phases of the machine learning process. Indeed, we've done this in Oracle Machine Learning, and we will continue to expand and improve. Unfortunately, not all phases of the machine learning process readily lend themselves to automation, at least not yet. For these, we'll likely see assisted machine learning, where we find full automation is not readily achievable. Today, AutoML is best applied to model building. Going forward, we can expect to see even more with respect to automatic data preparation, since that can take the lion's share of the machine learning project effort. We've shown the simplicity of model building with AutoML, eliminating repetitive tasks, which increases user productivity. Applying machine learning itself to the model building process can reduce the algorithm and hyperparameter search space, thus reducing compute time and cost. The need for AI and ML in the enterprise is clear. So assisting data scientists and enabling non-expert users to leverage machine learning to solve critical business problems makes clear that AutoML is a significant part of machine learning's future. Okay, so let's take a few questions. The first one that came up, which machine learning techniques are supported with AutoML? Well, in Release 1, AutoML in OML for Pi supports classification and regression. It's on our roadmap to expand into other machine learning techniques, for example, time series. And the same will be true for AutoML UI over time. Our second question is, when will OML for Pi and AutoML UI be released? We get this question a lot. OML for Pi is on the cusp of being released. It's currently in limited availability, and we expect the AutoML UI to enter limited availability relatively soon as well. The most I can say is that general availability will be available this fiscal year. Next, what compute resources are used to train models, and where do these models reside? Well, models are trained using the compute resources of Oracle Database or Oracle Autonomous Database. OML in-database algorithms eliminate data movement by building models within the trusted code of the database. This eliminates data movement outside the database, and the models themselves remain in the database's first-class objects. This allows users, for example, to grant model access privileges to other users and take advantage of standard backup and recovery mechanisms, among other features. Next, are there any features of Autonomous Database that AutoML leverages? I'd say there are many, but there are two important ones I'd like to highlight here. We have the in-database algorithms implemented in the database kernel, and so AutoML is leveraging those. essentially being a wrapper on top of the model building machinery we have built into Autonomous Database. Another Autonomous Database feature is autoscale. If you're not familiar with autoscale, it essentially allows your database to use up to 3 times the base number of CPU cores specified for your Autonomous Database to meet spikes in demand. As demand increases, autoscaling automatically increases the number of cores in use. As demand drops, the number of cores automatically decreases. So if you have multiple users or need more compute resources, additional compute will be dynamically allocated. Not too long ago, I wrote a blog at blogs.oracle.com/machine learning on the topic of model building performance on Autonomous Database. It's not specific to AutoML per se, but should give you a good idea of in-database model building performance. Next question. Can native Python models be deployed through this interface? The AutoML UI in Release 1 focuses on in-database models. However, OML Services not only allows in-database models to be managed and deployed using a REST interface, but also ONNX format models that were built using other environments. For example, TensorFlow-based models that can be converted into ONNX format can include image classification models as well, can be managed and deployed from OML services. A feature of OML for Pi we didn't cover in this section is called embedded Python execution, where you can store your Python models in the database and write a user-defined Python function to score using that data. Then you can invoke your function from an OML for Pi REST interface. As an added bonus in this, you can easily request the database to spawn multiple Python engines and have it automatically partition your data. This will feed each chunk to invocations of your user-defined functions in parallel on these Python engines. The next question is the AutoML functionality going to be available on premises? For OML for Pi, yes, OML for Pi with AutoML will be made available on premises after its release on Autonomous Database. However, the AutoML UI is expected to remain a cloud-based feature with Autonomous Database, so on-premises deployment is not currently on the roadmap, at least not for 2021. And it looks like that's it for questions.